We have done a basic introduction to the hash functions, and we have seen some simple ways to generate hash functions. But all those are pretty simple and very easy to break, and they are not so secure. So now we will have two short videos on two famous techniques which are very commonly used as hash generating functions, algorithms rather. One will be MD5 and other will be SHA3. They are in detail. If we do that, they are a little bit complicated, but we will try to do it in a very simple way and try to study the basic steps there. So MD starts for message digest, and it was invented by R. Rivest. It is the same R. Rivest who's co-inventor of RSA algorithm. The R in RSA is same Rivest here, and he actually proposed an algorithm which is called MD4, and then the improved version of that is called MD5. We'll discuss only MD5. And if you recall, for hash function, what is the need? That input should be of any length, output should be of fixed length. So for MD5, input can be of any length and output will be of 128 bits, and if you convert it into bytes, it is 16 bytes output. Now let's briefly describe the MD5 algorithm. The first step in MD5 algorithm is called padding bits. That is, we have input. See, input can be of any length, but it is very difficult to develop an algorithm which can take input of any length and produce the output of the same length. So what we will do is we will pad some extra bits so that the algorithm will always take input of a particular length. So the actual input you feed is of any length, but then you check that is it compatible with the algorithm. Okay, after we cover all the steps, it will be very clear what should be that input, how much length it should be, how many bits we have to pad. But the first step is padding some bits to make input compatible with the algorithm. Now what is that condition on the length of input? Right now just you read it, and when we will go through the full algorithm, it will become clear why it is so. The developers of algorithm have designed the algorithm such a way that input should actually be short of 64 bits of any multiple of 512. Now these bits added, how to add, what to add. So suppose the algorithm demands that you should add 20 bits to the input. So what should be the procedure? The first bit of those 20 bits should be 1 and all the rest is zeros. Suppose the algorithm demands that the input bits to be added should be 50 bits. So the first bit will be 1, all other 49 bits will be zeros. So this will be the first step 1, that is padding bits for MD5 algorithm. So we can summarize this step 1 like this. So we have the original message, and whatever be the length of original message, we will pad additional bits like this 1 0 0 0, and how many bits are needed, such that the total length is 64 minus the less than the multiple of 5 and 2. Okay, we'll elaborate on this with example later on. Let's move to step number 2 now. Step number 2 is called padding length. So in padding length, what we do is the length of original message is padded to the result from step number 1. So whatever we get from step number 1 after padding these bits, then the length of original message is padded to step number 1. How is that done? We express the length in the form of 64 bits. That is, the resultant string will finally be now a multiple of 512, because we are basically padding it. So we first pad it with the bits such that it becomes of length 512, 64 bits less than 512. Then we express it in the form of 64 bits. Before that, we pad the length of original message from the step 1. Now the resultant string will be 512 bits. Why is it done? So that the complexity of function is increased, especially the inversion of the function is not possible. Now what does it mean? See, we have some original message, fine, and we pad the bits such that the total length is 64 bits less than the multiple of 512, fine. And then we express the length of input, whatever be the number of bits of input, that we express as 64 bits. What does it mean? It means we reserve 6 bits. Sorry, it is 64 bit. So it means that 2 to the power 64, up to that, much different strings we can express. Okay, let me elaborate what it means. For example, let's say that after padding and with the original message, let's say the total length of original plus padding bits is, let's say it is 960 bits, the total length. Now 960, when expressed in binary form, what will it be? So this is the binary equivalent of 960. Now how many bits are there? 1 2 3 4 5 6 7 8 9 10. Now we add 54 zeros before this. Okay, 54 zeros, so that the total number of bits reserved for the length of input is 64 bits. Okay, it means that what can be the maximum length of input which can be accommodated? It is 2 to the power 64 bits, right? You see, with the help of 64 bits, 1 1 1 1 1 1 up to 1 1 1 64 length. So this can be the length of input, right? So 2 to the power 64 bits can be the length of input. So we are reserving. Now see, till now the original message plus padding bits were 64 bits less than the multiple of 5 and 2. Now when you add length of input as 64 bit, so this whole thing becomes multiple of 5.2. I hope this is now clear what the padding length step means. Now the third step is initialize message digest buffer. What does it mean? The entire message is broken down into the blocks of 5 and 12 bits. You see, if you have understood the previous step, now our total message, that is original message plus the padding bits plus the 64-bit binary string which represents the length of overall, this. So this total will be multiple of 5 and 2 bits, because original message plus padding bits were 64 bit less than the multiple of 5 and 2. Plus 64 will make this whole as a multiple of 5 and 2. So now the first step is the entire message is broken down into the blocks of 512 bits. Then we have 4 buffers which are used, and each of 32 bits. You can see that this buffer is same as the register we have seen in digital electronics, just stores 32 bits, and there are names given to it, so we name them as A, B, C and D. These are the 4 buffers. Now what is done after this is, now these buffers will be initialized. So initially they will take some fixed value which are fixed by the algorithm developers. Here are those values. So here are these values. A is equal to 0x6745, after this B is equal to like 0x E, F, C, D, A, B, 8, 9 and so on and so forth. These are 32 bits each. So these are the values, and later on we will see how they will be updated, these buffer values. Now we'll go for step number 4. Now when processing the blocks step, we observe that 512 can be written as 32 into 16. So what does it mean? So we can divide the padded message. It is basically processed in the chunks of 512 blocks, and each of the 512-bit block is divided into 16 32-bit words. Okay, 16 32-bit words. Here it's very important. And then after that, there will be 4 rounds of operation. What will be that? We'll come to that. And those operations utilize all these 16 sub blocks and the 4 buffers and other constants. Till now, let me summarize it, what we have in our hand till now. Okay, so see, one is that you have a message input which is a multiple of 512 bits. Okay, Then you have 1, 2, 3, 4, call this A, B, C, D, 32-bit buffers. They are initialized with some values. And this message is divided, now it can be divided into 512 blocks, and then each 512, suppose this is one sub block, so I will divide it into 16 sub blocks, each of them 32 bits. Now there will be 4 operations which will utilize all these sub blocks, these 4 buffers, and some other parameters which we will see. What are these constant values? It's an array of 64 elements with 16 elements being used for every round. So there are 4 rounds of some operations which we will see, and 16 elements will be used for every round, and 16 into 4 is equal to 64. So there will be 4 rounds wherein 16 elements from these 64 constant values will be used. Let's come to the notation. Let these M0, M1, M2 up to M15 represent the 16 sub blocks of the message, and T1, T2 up to T64 denote the constant array. This is notation now. Now let's see how in each of this process, in each of the operation, what is being done with these buffers, how are these 4 buffers being used. What we first take is, we have initialized all these buffers, so we take the value of these 3 buffers and we apply it to some non-linear function. Okay, we'll see what that function will be, and whatever be the output, we basically add it, there we do addition with what is stored in the buffer A. Now what we do is, we will take one by one these sub blocks of the message. Suppose we take the mjth of this. Now whatever we get here, the result here, this and this is also being added up. That is, we have first BCD, whatever is inside those buffers, we feed it to some non-linear function which you will see very soon. The result is out, the resultant of this non-linear function is added with the buffer value A. Whatever we get there, that is added with the jth block. Suppose if you are doing the operation on the first block, so M0 will be added, so on and so forth. Now we have a constant array. What will be the actual values of this, we'll see very soon. But what we will do now, we will add, suppose tk, with the result we got till previous step. I will repeat. First we take the data inside BCD the buffers, apply to a non-linear function. Whatever we get, we add that with the data stored in buffer A. Whatever we get there, we add that with the message block. Whatever we get there, we add that with this constant array. Okay, so steps will become clear later on when we will see what is the actual value of constant array, what is the non-linear function. Then the next step is, whatever we get here, we perform a circular shift. Okay, circular shift of the data. This is to ensure that there is sufficient complexity in the output digest. Then whatever we get here is added to the value stored in buffer B. So we do the addition of this output of circular shift with buffer B, and then whatever we get after addition is stored in B. That is, whatever was there in the B is replaced by what we get after this addition. And here comes the A, then C, and then D. Now the question remains, what will be stored in C, D, and A? So before we save this addition result in B, whatever was there in B is stored in C, whatever was there in C is stored in D, whatever was there in D is stored back in A. That is, concentrate here. See what are the initial values. So this B this 0xCFC is stored in C. Whatever is in C, this 0x98 full is stored in D, and this is stored in A. And in B, what is stored is the output of this whole process. Now, this is the operation done with one sub-block, suppose M0. Then, this final value of ABCD is taken as the input for next sub-block M1. And this whole process is repeated. Then, for M2, the whole process is repeated. Finally, whatever we get at the end of M15 will be the final output of message digest. And I repeat, what is the overall length of this? You see, if you go back to the previous notes here, A, B, C, D are all buffers of 32 bits. So there are 4 such buffers. So 4 into 32 is 128 bits. And after this 16 rounds, this 128 bits is the output message digest. So if you represent this whole MD5 algorithm as a box here, so you take a block of 512 bits and you are getting a constant block of 128 bits. Actually, your input is not 512 bits, it can be anything, right? And what we are doing is we are basically checking what is the length of input, and then we are padding it with the number of bits, starting with 1, then 0, 0, 0, such that the total length is a multiple of 564 bit less than any multiple of 512. Okay, and then we add 64 bit string which represents the length of the total message, and then that is fed to MD5, and the whole steps are here, and we get 128 bits output. Now remains the main step. What is the non-linear function here? So these are actually 4 rounds of operation, each of them utilizing all 16 subblocks. Let's see what it is. Here are those 4 rounds. Here are the 4 rounds. Round 1, we do B and C, whatever we get there, or that with not of B, and then D. So if you go back to this, so whatever is stored in B, C, D and A, I demonstrate one step. So we first take B and operation, B and C, then we perform the not operation to the B, then we do the OR operation between these two, and then whatever we get, we do the AND operation with this. So this is what we get in the round 1. So this is what we will get in round 1. Similarly, in round 2, we do B and D, then OR with C and not of D, then we do XOR in 3rd round, and in 4th round we first take not of D, then OR that with B, and then XOR with C. Since there are 64 constant values and you are having these 4 non-linear rounds, so 4 into 16 is 64, correct? Since we are having 16 sub-blocks, and for each sub-block we are having 4 such rounds, so it means we need 4 t values. So 64 t values will be used for a complete 512 bit block. Now one more point. What is this t vector? How is the ti value chosen? What we do is first, whatever be the value of I, so I will be from 1 to 64, we compute the sign of I, okay, taking this in the radians, then take absolute value, okay, so that negative values are avoided, then it is multiplied by 2 to the power 32, and the integer part of this, whatever we get, is taken as t. As an example, let's take I is equal to 1. So what is sign of 1? Around 0.84. So 0.84, absolute of this is same, into 2 to the power 32. What will be its value roughly? So it is around 1.68 into 10 to the power 32, nearly that. So if it is a fractional, we will just take the integer value, and that is stored in the t. So all this is done to increase the complexity of algorithm. So now the algorithm is complete. Definitely it's a little bit lengthy, so I will briefly revise it in the next video, and also give a one small example which will clear all the confusions about MD5. Thank you.